video, we will be discussing about trapping rainwater too. Given an m cross n integer matrix height map representing the height of each unit cell in a 2D elevation map, return the volume of water it can trap after rain. So what they are saying is that in the input, we are given a 2D integer array which is height map, which represents the height of each of the cells, right? So basically you can see in this particular diagram that we are having some cells which are having some height. So if you see this first cell is this one, this is representing this block and this is representing the first block. So if you see this height is 2, so here we have a block of height 2. This is 3 and 3, so these are the blocks of height 3. Then 2, this one, 3, this one, and 1 is this one, right? So this is how it is represented through the diagram. Now, what we need to identify is that after raining, how much amount of water can be stored between these cells, right? So here I have drawn a top view of this particular matrix, maybe, right? So here we have a cell of height 1, then a cell of height 4, and so on, right? So this is what I have drawn. With the help of this, we will try to identify the answer. I must say this is a very tricky question. It's very difficult to come up with the intuition for solving this, but let's try to understand what we can do over here. So see, if let us suppose that I have a cell whose height is 1, right? And then I have some of its neighbors cells, right? Let's suppose the height is 2, 2, 3, 4. Now, when it rains, can this particular cell store some amount of water? And if yes, then how much amount of water can it store? So if let us suppose here we store 1 units of water more. If we'll store that, what will be its height? Its height will be 2, right? Here we can consider this is a wall of height 2, this is a wall of height 2, height 3, height 4. So if I store anything of height 2 over here, then it will not overflow from any of the sides. But if I make its height as 3, right, if I add 2 units of water, then in that case what will happen is that that one extra unit of water can either overflow from this side or from this side, right? So what did we understand? That the units of water that can be stored in this particular cell depends upon the heights of its neighbors, and that too on the smallest height of the neighbors, right? In the neighbors here, the smallest height is 2. So the amount of water to be stored in this particular cell depends upon this smallest height 2 of the neighboring cells. So keep this thing in mind that we are considering the smallest height of the neighboring cell, right? So now here we can store 1 units of water because the minimum was 2. 2 minus 1, 1. So 1 units of water can be stored over here. But if let us suppose that instead of 1, the height was 3. Now can I store some amount of water over here? No. Because if I will put anything over here, it will overflow from all the sides, right? So here the smallest height of the neighbors was 2. And the height of this cell is already greater than the height of this. So we cannot store anything over here, right? But does the height of this particular cell, or basically the amount of water that it can store, does it only depends upon these neighbors? If you come here, so see, if we come here, if we see at this particular cell, right? If I store 1 units of water here and in this I store 2 units of water, if I do so, then this height will also become 3, this height will also become 3. Now if we see here, height is 4, 3, 3, 3, 3, 3. So then that means yes, here I can store 1 units of water here and 2 units of water here, right? But if let us suppose that here instead of 3 we had a 1. Now if I ask you, can I store 1 units of water here as I did before? See, if I will do so, then what will happen? This height is smaller, so that 1 units of water will overflow here, right? Now earlier when here 3 was present, so when 1 unit of water overflowed here, then this boundary didn't allow it to overflow further. It remained in this particular cell only. But since now we have a 1 over here, so as soon as the water will come here, it will overflow here and then it will come out, right? So from this, what did we understand? That whether some amount of water can be stored in this particular cell, it not only depends upon its neighboring cells, but it also depends upon the neighbors of the neighboring cells, right? So this is kind of progressive. We need to consider the height of the neighbors of the neighboring cells as well, and so on, right? So if we go ahead and do that for each and every cell, then it will be very inefficient, right? So we will have to think of something else, right? So see, now if I ask you, can this particular cell store some amount of water? Here this is having height 3, this is having height 4, both are greater. So this can store 2 units of water. But here we are not having any boundary. So this cell cannot store any water because it will overflow. It is not having any boundary, right? So from this, what did we understand? That whatever are the boundary cells, those cells can never contain any water, right? So this is one conclusion that we made, that the boundary cells will never contain water, right? So since we know that these cells are not storing anything, so with the help of these, we will identify that what amount of water can these cells store, right? So what we can do is that we can take all of these cells into consideration somewhere, right? So in some data structure, we will store all these cells and then we will consider each of the boundary cell one by one. Now my question is that which cell are you going to consider first? We will be considering the one which is having the smallest height, because as we saw over here that the amount of water depends upon the smallest height of the neighboring cells. So that is the reason out of all these boundary cells, we will first consider the one which is having the smallest height, right? And since every time we need the smallest height, we can maintain a data structure, maybe a min heap, right? In this min heap, we can store all these boundary cells and it will always give us the one with the smallest height, right? So all of these will be stored in our min heap, right? So now this will give us the one with the smallest height. So let's suppose it gave this particular cell 1, right? Now, what are the neighbors of 1, 3 and 4? Now, if you see, can these two cells store water? No, because they are the boundary cells, right? They cannot store any water. So we cannot consider anything for 1. And how are you going to identify whether these are the boundary cells? Because they will be already present in the min heap, right? So what you can do is that whenever you are pushing anything into the min heap, you can mark it somewhere, right? So we can also take a visited vector, 2D vector, equal to the size of this matrix. And whenever you are pushing any cell into the min heap, you can mark it as visited. So for this one, its neighbors are already visited, so we cannot do anything. We will just remove it from our min heap, right? Now, the next cell having the smallest height would be, let us suppose, this one. Again, its neighbors are already visited, so this will be just removed. Next will be this one, right? Now, these two neighbors are already visited. This is the neighbor which is not visited yet. Now, if we see over here, this is having a height of 1 and this is having a height of 3. Can I store some amount of water here? No. Why? Because if I will store anything, it will overflow from here, right? So whenever the height of this cell is greater than the height of the boundary cell, then we cannot store anything over here, right? So we will move forward. But since now we have considered this, we will push it into our min heap, right? And if you notice one thing over here, that the first time that we have encountered this cell, we encountered it with the neighboring cell having the smallest height. What are the neighboring cells of this three? 1, 1, 2, and 2. What is the smallest height? 1, right? So when we encountered this particular cell for the first time, we encountered with the neighboring cell which was having the smallest height, that is 1, right? And that is the reason we are maintaining the min heap and we are considering the smallest heights first, right? So if here we are considering the smallest height first, so with this, if we are not able to store anything here, then with these also we will not be able to store anything, right? So that is why we will push this also into the min heap and it will be marked as visited. So you can consider that your boundary has become something like this, right? This one has been removed. You can consider something like this, right? So now we are done with all the ones. Now 2 will come. So let's suppose if we consider this 2, so its neighbors are already visited. So this will be removed. Then we can consider this 2. Again, the neighbors are already visited. So this will be removed, right? Now is this 2. This is already visited. This is already visited. And this also we have pushed into the min heap and also visited, right? So this will also be removed. Next, we will come to all the 3s. So if let us suppose we consider this particular 3. So this is visited. This is visited. This is not visited, right? Now if you see over here, this 2, right? This 2 is having height 2 and this is having height 3, right? Can we store some water over here? Yes, we can. because the height is smaller. 3 minus 2 is 1. So we can store 1 unit of water over here. So we will take some variable water and we will update it to 1, that okay, we have stored 1 units of water over here. And now since we have stored 1 unit of water over here, its new height will become 3 now, right? Its new height will become 3 and this will be marked, right? Now, although this was having a height of 1 on its right, but this will also be considered in our min heap as we move forward, right? So now let's consider this particular 3, right? For this is visited, this is visited, this is not visited, right? Now, can this store some amount of water? Yes, because its height is smaller than 3. So how much amount of water can it store? 3 minus 1, that is 2. So in water, we will add 2. 1 plus 2 will be 3. And what will be the new height of this? The new height will be 3. This one is removed now, right? Then if we consider this particular 3, right? So these are already visited. This is not visited, right? Can it store water? Yes, because the height is smaller. And how much? 3 minus 2, that is 1. So we will add 1 in the amount of water. So this will become 4 and the new height of this will become 3. This one will be removed, right? Then we have this 3. This is visited. This is visited. This is also visited. So this will be removed. Then this 3, all the neighbors are visited. This will also be removed. Then these 3, so all the neighbors of these cells are visited. So these will also be removed. And then we will come to 4s. Now their neighbors are also visited. So they will also be removed. And finally, the total amount of water which is stored in this particular heights map is 4, and this we need to return in our answer, right? So basically through this min heap and visited array, we are able to identify that in a particular region, how much amount of water we are able to store. Here we stored 3 units of water, here we stored 1 units of water, right? So since for each of the cell we were having multiple directions and it was dependent on multiple cells, that is why we went for a graph approach over here, right? So I hope you understood the intuition. So simply what we can do is that we can take a min heap, right? And we can insert all the cells. So since we want the cells with the smallest height first, so in the min heap, we will have to store 3 things. One will be the height, right? One will be the row of that particular cell and one will be the column. So maybe we can create a vector and then we can store these 3 things, right? And then we can take a 2D vector visited to mark the cells, right? And then what we can simply do is that while our min heap is not empty, we will take the first element out or the top element out, and then we will consider all of its neighbors. If the neighbors are already visited, we won't be doing anything. And if they are not visited, then first of all, we will mark them as visited, right? And then we will check, can they store some amount of water or not? So if their height is less, so yes, they can store. If not, they cannot store, right? Accordingly, we will update this water. And then whatever is the maximum height, basically, if I considered this particular 3 and its neighbor is 2. So for this 2, what will be the height you will be storing? Whatever is the maximum height of these 2, which is 3, that we will store in our min, right? So this is what we need to do. Now let's quickly look at the code. So first of all, let's take a variable water to store our answer. Then let's take the size of the heights map vector. So it is an m cross n, right? So m will be equals to height map dot size and n will be equals to height map of 0 dot size, right? Then we need to create a vector for the directions. So it will be vector, vector and directions. And what are the 4 directions that we have? Like the neighboring cells, top, left, right and bottom, right? So we can do 1 comma 0, then minus 1 comma 0, then 0 comma 1 and then 0 comma minus 1. So these are the 4 directions. Then we need to create a visited vector. So it will be vector, vector, bool, right? We can name it visited. Its size will be m cross n. So vector, bool and then n comma, initially we can keep all the values as false. And then we need a priority queue, right? Basically a min heap. So priority queue. And since we need to store 3 things over here, it's better that we take a vector, right? And since we need to create a min heap, by default it will create a max heap. So we will also have to write vector, vector int comma greater and then its name PQ, right? So now we have initialized all the things that we need. Now let's start inserting the boundary cells into our min heap. So we will run a for loop of I starting from 0 going till m and then I plus plus. Inside this we will run another for loop of j starting from 0 going till n and then j plus plus, right? Now what are your boundary cells? That if I is 0 or if j is 0 or if I is equals to m minus 1 or j is equals to n minus 1. In all of these cases, you are having the boundary cells. So we will be doing two things. One is pushing into the priority queue and the second is marking it as visited. So pq dot push, since we need to store three things. First is the height. So in the height map, the index I comma j, and then the row which is I, and then the column which is j. And then for marking it visited, so in the visited at the index I comma j, we will make it true, right? So now we have pushed it. Now we will apply the BFS, right? See, we are using a priority queue, right? This is kind of a BFS, that while our PQ is not empty, right? What we will do, we will take the first element which will give us a vector. Let's name it T. So it will be PQ dot pop, and then we can pop it, right? PQ dot pop. So this is giving us three things. One is the height, which will be present at the 0th index. One will be the row present at the first index, and one will be the column which will be present at the second index, right? Now we need to consider the neighbors, the four neighbors of the cell. So for int direction, or it will be auto since it is a vector. So for auto direction in directions, right? So our new row will be whatever is the current row. In it, we will add whatever is present at the 0th index in the direction. And then the new column will be column plus the first index in direction. This will be the new row and column, right? Now we need to check whether this row and column is valid. That is, it is within the range of our matrix and it is not yet visited, right? So if nr is greater than equals to 0 and nr is less than m, and nc is greater than equals to 0 and nc is less than n, and in the visited the index nr comma nc is false, if this is the scenario, only then we will consider it, right? So now the height of the current cell is stored in h, and the height of this new cell, let's name it nh. So this will be in the heights map, whatever is present at the index nr comma nc, right? Now we need to check that if this height, the height of the new cell is less than the height of the boundary cell, then that means we can store some water over here. So in the water, we will add the difference, right? H minus NH, right? And then since we are visiting this cell for the first time, we need to mark it as visited, and we will also push it into the priority queue. So what is the height that we will be pushing? We will be taking the max of H comma NH, right? And then the indices will be NR comma NC. And then at the end, we can simply return the amount of water. Let's try to run this. So here it will be T and T. Let's run it again. I hope there are no other problems in the code. Yeah. So now if you see over here, we are running a loop m cross n times for storing the neighboring cells, right? And then we are applying BFS over here. Now here also each of the cell will be pushed into the priority queue exactly once. So we can consider that it is running m cross n times, right? And then inside that we are doing push and pop operations into our priority queue, right? Now what is that going to take? Log n time. And what is the maximum size that our priority queue can have? M cross n, right? So we can say that the time complexity in this particular case will be order of n into m into log of n into m, right? And what will be the space complexity? So space complexity will be order of n cross m, because we have taken a visited vector which is of this size, and we have also taken a priority queue for performing BFS that will also have max to max these many elements, right? So let's try to submit this now. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.